about starting from how to take the FTIR data and process it in Excel and then deconvolute the whole data. So this is how your FTIR data will look like. Okay, so these files come in the DPT format. So you have to open that. It will be opening in a notepad, and you have to copy it. Control A, Control C, and go to Excel file and paste it. Now you can see the data has not been separated. That means the wave number and your transmittance data, they have been just separated by comma. What you need to do is to separate them in two columns. So what you need to do, already the data has been selected, go to this data tab and go to text to columns. Here click on next, then select this comma and next and finish. So your data has been separated into two columns. Your first column is its wave number and this is your transmittance value. Now you have got two of your data, and for the deconvolution purpose you need another data, that is absorbance values. So how to derive absorbance value from the transmittance? The formula is it's 2 minus log of this particular value. Click enter and then populate the rest of the cells. So now you have got all of your data that you need to need to plot and require it for deconvolution process. So I hope you have started using this Origin software. So I've created a new folder. Now I'm going to create a new workbook. So first let me show you how the FTIR data has to be plotted. Just normal FTIR data before deconvolution and all. What you need to do is to select these data, wave number and the transmittance value, paste it here. So your X column, it's representing the wave number and this Y column is the transmittance value. So what you need to do is select both of the columns, and here you have an option line graph and click on line graph. So this is how your FTIR spectra for a particular sample will be looking like. Usually what we do is we here you can see the graph has been from starting from the lower wave number till higher one. You just can convert it, I mean alter it. So double click on the x-axis and a window will open. So here you can set many of the things, but for now we are going to change the scale. So for changing the scale, click on the scale option, and here it's starting from saying that it start from 250 till 4500. So you just need to alter it 250, and this is how most of your FTIR that has been given in some research articles, it will be looking like. Now some further processing of this can be, for example, here you have some gap between 4500 to 4000. So you don't need this particular gap, so you need to remove that gap. Again double click on the x-axis, the same window will open, and you just need to start it from 4000. Here it's starting from 4500, right? So just make it 4000 and the gap is removed and it's a complete spectrum. Nothing has been removed or deleted, just the gap has been covered up. Okay, now what you can set is here you can write the access titles. So it will be wave number, which is in centimeter inverse here it's your option for superscript, so I want my -1 to be superscript. Complete it. We're done. And same goes for the y-axis. It's the transmittance value, and it's in arbitrary units. So now we can change. You have to change the font because most of the font style that we use in our graphs is the Times New Roman. So click on this particular axis title, and here you can set the font, set to Times New Roman, and you can also increase the font size. Let's say I'll make it 26. If we double click it and just click Control B, and it will be in bold. So the same for other axis. Okay. So also you have to change the font for these axis numbers. It should be also in Times New Roman, and bold it, and just let's say it's a 22. So everything should be uniform and consistent, even if it's font size or font style. Now you can see this graph is looking like the line is very thin, right? So you can also increase the width of this particular graph. Go here and select 2. Okay, now it's pretty much visible. Okay, you can also select the graph, and you can also change the color of this particular. Let's say we can set it to blue. Okay, so this is a whole spectrum of a particular sample. Now what you need to do is to export this particular graph as in a format of an image. Go to file, go to export graphs, open dialog, a window will open where you can change the file format and give the name of the graph. Here there are several file formats, but we'll be saving in TIFF format, tag image file. And let's give a file name, FTIR graph. And you can also set the path where you want to keep your graph, and click OK. So here you got the message, the graph has been exported to this particular location. Let's check whether it's yes, it has been already exported. So here it's a full graph. Okay, so you don't need to take a screenshot or just cut the screen and save it as an image. You can directly export the graph as image files. Okay, so this was how your normal FTIR graph should be looking like. Let's move on to the deconvolution process. So before deconvoluting the graph, we have certain steps that we need to perform. First of all, let's say you have to plot the graph, how the absorbance graph is looking like. So you have your absorbance data, and I took the wave number data that will be same, so there will be no change. And you have to convert this axis to x-axis. Here you can see it's written dy, that means it's still in y-axis, and we want our wave number to be in x-axis. Select this column, click x, so it will be set as x-axis. Now select both of this column, repeat the same steps that I have mentioned earlier, and here your absorbance data is just has been rotated, you can see. Now the thing is, for the FTIR deconvolution part, you don't need to deconvolute the whole graph, rather you need certain areas or regions that that need to be deconvoluted. So among this, like what I did is I deconvoluted three different regions: this water region, amide region, and last is the starch region. So you need to pick a certain area and extract it from the whole graph, and then you have to deconvolute it. Let's say we will be deconvoluting the starch region, and the starch region usually ranges between 1080 till 950 centimeter inverse. So we have to pick that particular data from our original data. So here it's our original absorbance data. Now whatever you will be working for the deconvolution process, you will be working on the absorbance graph, not the transmittance graph that we have plotted earlier. That was the transmittance graph, and this particular graph, it's the absorbance graph. So for your easiness only, you can use this transmittance curve, sorry, absorbance curve. So we'll be extracting the starch portion, which starts from 1080, let's say 1081 till 950. 950. Now again plot this particular curve, the selected data. Now this is your um, extracted region of the, for especially for the starch region. So now before deconvoluting, you have to make sure that the baseline has been corrected for this graph. Here you can see it starts from here but ends up somewhat higher. So you have to subtract this baseline and get it to an equal point. What you need to do is to go to analysis, then go to peak analyzer. In peak analyzer, there will be subtract baseline. You have to select that, click on next. Now the baseline mode should be user defined. We will be deciding which points we need to take to subtract the baseline. Now already these points have been given here. In case this particular second red dot comes in between here or anywhere in the graph, you just need to drag it to the end. Now click next. So the interpolation method will be spline, and again click on next and click on subtract and finish. So uh, the subtracted the subtracted baseline and the curve will be appearing here as two new columns. Here you can see two new columns have been added here. So this is your subtracted baseline and this is your uh, graph that you require. So again plot this particular data as a file. So now you can see the baseline has been corrected. Okay. Now you have to perform the deconvolution in this particular graph. So as always I say, start the graph from the higher wave number to lower wave number. Just alter the scale. Okay. For the deconvolution, go to analysis and there will be peaks and baseline option. Go to multiple peak fit and open the dialog. So the here it has been indicated to mention the peak function. So there are several peak functions available, but the Gaussian peak function is usually used for deconvoluting this type of graphs. Click on OK. Then you have to select the peaks. So the first thing that you need to know about this deconvolution process is why are you going to deconvolute a particular graph? Because you are already having some initial peak. So what is the reason behind the deconvolution process? First is there are many hidden peaks that you cannot identify in a particular graph. First of all, the deconvolution process will reveal those uh, hidden peaks. Secondly, it will also give the data regarding how much individual hidden peaks is contributing to the whole graph, how much area it is consuming, how much width it's giving, and at what particular location, at what wave number. So certain peaks, for example, saying if you uh, deconvolute the protein region where amide bonds and related molecular vibrations appear. If you select a particular peak and then you deconvolute it and you get some hidden peaks revealed, then the peak position at which that particular peak has been revealed at a particular wave number, it's related to certain secondary structures of the protein. Okay, for example, the alpha helix, beta structures, random coils, these if these kind of secondary structures are present in your sample, then those peaks will be revealed after you deconvolute the amide region. So for alpha helix, beta sheets, there are particular range of wavelength between which the peaks will be shown, not above beyond that particular region. Okay, so as I am doing the deconvolution for the starch process, so those are related to the hydrated crystalline or amorphous structure of the starch. So each whatever peaks will be revealed in this particular deconvolution process, it would be related to there would be certain significance associated with those peaks. So now what I need to do is to select few peaks. First of all, I don't know where the peaks can be related. Or just because I have already performed these deconvolution process, so I know there will be three peaks in this particular starch region. For other regions like amide or the water regions, the number of peaks can be even more. So you need to select. So let's say here it is, there might be one peak, and here another peak, and another peak here. Okay, now go to open NL fit. So this deconvolution process is not a single step process, rather lot of iteration happens. This particular function will try to fit different types of different hidden peaks, and it will iterate the process unless and until it finds a perfect fit for the graph. So here you have two options, one iteration or fit until converged. So this second option, that is fit until converged, uh, if you select this particular option, it will continue the iteration process unless and until the fit has been done. First of all, let's see how the single iteration will do. See, the peak positions are changing. For every iteration, the positions are changing. So you just cannot keep on clicking on the single iteration. Just let's say we are doing it fit until converged. Now you can see the last message has been given. Fit converged, your chi-square tolerance value is 10 to the power minus 9 was reached. So this is a parameter which will say that your fit has been done perfectly. If the value is something else or less than that, and if there is some error messages appearing, that means the deconvolution process has not been performed successfully. There has been some mistakes, or the parameters has been over I mean the peaks have been over parameterized, in the sense that you have selected numerous peaks than it has. I mean, in the original graph, whatever peaks are there, you have selected more than that. So it wouldn't be converged. I mean, the fit wouldn't be converged in that case. So here we have taken the optimized number of peaks, that is the three peaks. So the converged has been performed successfully. Now click on OK. Now a data table will be shown here regarding the details of those peaks. So this particular graph that this particular region which we have selected from the original FTIR graph is containing three different hidden peaks. So you have all the data here, like the y position, x position, like the wave number. So the first peak which we have obtained is at 1042 centimeter inverse. Similarly, the second peak and the third peak were obtained in 1012 and 988 centimeter inverse. Apart from this table, you go to the book where you have your all the original data. Now you can see some extra sections has been created in this particular window. Now see, here you got all of your data. Now what you can do, if you want to uh, copy into a Excel file, just copy the table, go to your Excel file, and you can copy it again. Copy the table. Okay, so all of your value has been pasted, transferred here. So among this, what values do you need? So you, first of all, you don't need these standard deviation values. Okay, you don't need these standard deviation values. Neither you need the width or the statistical analysis of those related to those peaks. What you need is these two values, your XC value and the area value. Okay, and you will be further processing the values. Further process the data using these values. So this was all about the deconvolution process. Okay, I hope you got it. Uh, Another thing that I need to tell you is I have performed the deconvolution process just once. Okay, so for each of your sample, you will be having replicates for that particular sample. So let's say you are having three replicates for your sample. Now, three replicates means in one replicate in one FTR graph there will be three regions. So that means for every region you have to perform this deconvolution process thrice. Okay, so let's say for my sample 1 I have taken one replicate and I have deconvoluted this starch region. So the rest of the replicate would also be having the starch region. You have to replicate those also, and other regions like the water region and amide region. So there is a the process is a bit easy, but it will be take some time to complete the whole thing. Now what I need to show you is I had some of the data, previous data regarding a sample, and I had five replicates, A, B, C, D, and E. And I have the XC and A value for all the replicates, and I had five peaks. Okay. Now what you need to do, as you have to present the data in a form where you have to give the data as a percentage format. So here you can see, so here the data has been plotted as a content percentage. So how to get that particular percentage? Now see, you have five peaks and you have area values. Okay, now you have to make a sum of these particular these area, and here the overall area is 69. And now you need to take the percentage, like how much percent this particular value is contributing to the whole. So what you need to do is you need to divide this value with this and multiply by 100. Here you can see I have wrote the formula. Put the formula and you will having all the values in the form of it's in percentage. Okay. Now similarly for different replicates you will be having different peaks and you have to make a table that okay peak 1 is having in replicate A peak 1 is taking 8%, in replicate B the peak 1 is consuming 8.5%. So the over average value is kind of similar, not same but similar. Okay, so obviously for replicates the data will vary. So peak 1, peak 2. So now you have listed those values to take a average and the standard deviation. So the same thing goes for peak 2, 3, 4, 5, 4, however, how many whatever peaks you have. You just
Number of peaks may differ for all different samples.
yes. If for let's say in my sample OG, I have 5 peaks, but in sample OG1 or OG2 or any rest of the samples, either peak 3 would be absent or peak 4 will be absent. Okay, so that can happen. So you have to consider those peaks which are existing in most of the samples. Okay, so now you have to plot this as a bar plot in the origin only, and you will create a graph like this. And later on you can also perform the statistical analysis using the average values. Okay, now this is for the water region. So I had 4 peaks, and for the amide region, beta sheets, alpha helix or beta turn content, I had a few number of peaks and I had to be very selective about it. So I just had to list out only these three. But apart from there's random coils and some other structures does exist. So this is the starch region that the graph that we plotted now only. Okay. So this was all about your deconvolution process.